those are just definitions of things, okay? So we'll just choose, as I say, okay, philosophically you can argue whatever you want, which one is better, but in practice it's going to be clear from the problem which one we are going to do. And so then that line of charge problem that you already done in freshman physics or in sophomore physics, whatever, let's quickly review because I want to emphasize some aspects of the physics here, okay? And also very, very important is to put into play practicing with this notation, which we are going to use during the whole semester. And so, all right, so for that line, which I consider to be a review, so I'm going to move fast, everybody has done that problem before. So we have a line of charge with a uniform charge lambda, so lambda of r prime now doesn't depend on r prime anymore. Basically you have the same charge distributed all over the line, and then we can actually choose arbitrarily for convenience that line is going to be sitting on the z-axis. Why not? Okay, we can just tilt our frame of reference so that the z-axis is there. And so our problem then is going to look like this. Okay? Okay, so this is our z-axis. Now, clearly there is a high symmetry in that problem because if you look around that axis, the result should be the same, okay, with what do you call it, cylindrical symmetry. Yes, and so that means the following, that if this is the z-axis and this is the x-axis, I can actually solve the problem along the x-axis. Well, there are two comments. Not only there is cylindrical symmetry, but there is also translational symmetry along the line. So in other words, yes, assuming it's infinite. Yeah, very good point. Turns out that the finite problem also can be solved, no problem. Okay, and I'll give you some exercises for that. But let's assume if it's infinite, yes, then you have translational symmetry, and basically then all that matters is the distance to the line. And so for that reason, I can concentrate on solving my problem on the x-axis. If I do that, I solve the problem completely. Okay? So for that reason, we are going to take the observation point here, the test, the probe, the observation point, whatever you want to call it, there, and this line is going to be our source. So basically any point on that line is going to be a source. So let me take a little small element there along that line, and that's going to correspond to one of the r primes. Okay, so starting from the origin, then all my r primes are going to have a z component, and all of my observation points are going to have only an x component, correct? So in pictures, this is what I'm talking about, that this point over here is r prime, and this point over here is the point r. Okay, so all we need to do is to realize where are our sources and where we want to measure. Once we have that, everything is almost done. Basically, the only thing that is, that's why I was telling you to be very careful in your writing and the question of notation. We cannot make mistakes, even in very complex problems. This is simple, but in very complex problems, if we approach it the same way, maybe we cannot solve the problem because it's so difficult, but at least we are going to establish the problem in a very good way. And so, in this case, the vector r, of course, naturally can be written as a point of coordinate x along the x direction, now explicitly. And this point r prime always will be z along the z direction. Okay? I don't need to make any picture, anything. You will see, because I can actually take care of everything just by using the expressions we have. So for example, in this case, of course we are going to use this expression, and let's say that I want to find the electric field at the observation points, okay? It just happens that the electric field can be obtained at any location r, but clearly, for us, the only coordinate that matters is x, because of the symmetries. Okay, so clearly, in this problem, it makes sense that E of r is equivalent, not equal, but to E of x. Okay, it's not the same. Of course, I cannot write an equal because the vector electric field here is not the same. So if I look from the top, the electric field will rotate. Okay. But fine, let's say that I want to find the electric field there. Once we have it, we have all the important information. So that electric field, according to that equation over there, is 1 over 4 pi epsilon 0 integral, okay? And always, we don't need to worry about the integral until at the end, okay? So we have to do an integral on a curve somehow, but we don't worry about that. Once we do the integrand, it will be obvious what to do, okay? So we have lambda dl prime divided by, let me put the dl prime at the end, r minus r prime, which is xx minus r prime cube times r minus r prime, which is x minus z. All right? So this element, dl prime, so we have to see at the context, but dl prime is nothing by definition in an integral, in a line integral, but the absolute magnitude of this. Right, dl prime, yes, is that clear? How do I know that that's the case? Okay, so imagine that you are doing a line integral of a curve to get the length. All you do is you sum the little segments. Yes, so if you have a curve, you can actually consider the vectors as you walk across, but what matters to get the length is the magnitude of each small element, okay? So the dl prime in a line integral has this meaning, and if I look here, what is that? Well, but the magnitude? Just dz prime. Well, in this case it's dz actually. That's okay. Let me, hold on a second. This is not a problem, okay? I'm going to do that in another problem the same. So r and r prime stand for observation point and source. But in this particular case, I just happen to choose r prime z, not z prime. Fine, no problem, because you know there is no confusion there. Okay, we need to see, because some of you may say, okay, use z prime. Yeah, I can, but it doesn't really matter. Okay, so let's stick to that since that's what I wrote. Okay, so dr prime is dz. Okay, so I have to finish this thing here. Okay, so you see this z is consistent with the z's that I took before, so everything is fine. So I need to do an integral in z. Okay, that's when, after I finish writing the integrand, I go back to the integral symbol itself and I figure out my limits at the very end. Okay, so for this particular case, my line goes from minus infinity to infinity. But as I said before, this problem also can be solved in a finite line, and so for example the line could go from 0 to infinity or from 0 to a. All those problems can be solved. Okay, you will see why, but all right. But in this particular example, when it goes from minus infinity to infinity, then that's what we have. Okay, so now the explicitly the bottom, the denominator, is the magnitude of that vector. And you see, we don't need, I haven't drawn any picture. I don't need to. Because this way of writing the notation basically automatically tell us what to do. So I have a vector, and all I need to do is to compute the magnitude. Okay, so the next thing is then one of 4 pi epsilon 0, integral from minus infinity to infinity, lambda dz. All right, the magnitude is the following. The magnitude of a vector is the square of the magnitude added up, square root of that. Correct? Yeah. So, but I have it to the third power here, so I have to keep that. So it's going to look simply like x squared plus z squared, square root of that to the third power. Break. It's okay. Okay, we are almost done. Okay, agree with that? Is that okay?
What we did downstairs, we just changed it.
I computed the magnitude of the vector. The vector is xx minus zz, so the magnitude is x squared plus z squared, square root.
With the direction get cancelled.
Yeah, because I'm only, exactly, that's why I'm using just the notation, because it tells me, do the magnitude. Yeah. So that's what I do. All right? Now very quickly, we have 5 minutes, look at the following. In this integral, we really have 2 integrals. And that's great, because we are looking for a vector. So in general, we should have 3 integrals, one in x, one in y, one in z. It's a vector, okay? But okay, so let's look at those 2 integrals. The integral in z, so this would mean that the electric field has a component along x and a component along z, correct? Fine. The integral in z is going to look like this, z divided by x squared plus z squared. So remember odd and even functions? So what would that be? Odd function, right? It's odd. So the integral between minus infinity and infinity of that is 0. Okay, so this term here is going to give us 0 integral. Okay, that's an odd integral. Okay, that actually makes us very happy, because if we are sitting on the x-axis and we see a lot of positive charge on top of us, and the same amount of positive charge at the bottom, we don't expect to be feeling a force in the vertical direction, only be pushed away or pulled in, right? Yeah. There is no, because the problem is completely symmetric. So this is really very good result in that sense, and we are left with this integral. Since we're integrating in z, x is a constant that can be pulled out. Okay, and so now we get an odd, an even function in this case, so that's not going to cancel. All right, so do this. 1 over 4 pi epsilon 0. Actually, the lambda can be taken out, and the x direction also can be taken out, and then we end up with this. Now, of course, the x I can take out if I want, but let me leave it there for a moment, okay? So, what I want to do, I'm integrating in z, and inside this, one thing I want to emphasize, and every time that you can try to do it, which is pretty much every time, if you think about it, try to reduce the problem to a non-dimensional form, okay? And I will do this, and we will finish the class. But what I mean, you will see what is the advantage of doing that. So since I'm integrating in z, basically in this particular example, it reduces to a change of variables. But I'll do it just by looking at what's going on. So I have an x squared plus z squared, okay? Those are lengths. So since I'm integrating in z, the natural thing for me to do here is, so if I take this x squared, which is just a constant as far as the integral is concerned, when I take the square root of that and I raise it to the cube power, so I'm going to get x cubed here if I put a 1 here, correct?
Yeah.
Okay. So if I have an x squared here, suppose that the z doesn't exist. X squared, square root x, x cubed. So this x squared to that power is an x cubed. So I'm going to pull it down, out. But then I have to put a 1 there, but this is not right now, because I remove an x squared. So it has to be z over x squared. And it's exactly the same thing that we had before. Okay? Now, this x cubed, second, since I have a z over x here, I'm going to put a z over x here, the differential of z over x, but x being a constant, I need to multiply times x also to have the same thing.
You added an x, multiply by an x over there?
I put an x here and I divide it by x here because the differential of something times a constant is the same. So at the end of the day, there is an x squared up here and an x cubed here. Now I'm going to take out the x finally. So I'm going to get rid of this one. I'm going to get rid of those two, and I'm going to put a 1 over x here. Okay? Now I'm going to make a change of variables. Okay? I could have done it. So I'm going to call the ratio z over x some letter whatever. Okay? Call it s.
You also divided on the bottom that we did before.
Wait. I basically. Okay? So we end up with that. So,
X squared is x cubed.
because I had an x squared up here and I had an x cubed there, so x cubed. Yeah, move it out. Okay, so this is basically, look at what happens, okay? So in mathematics.
You had another x on the z.
Yeah.
You really had x to the fourth on the bottom, x squared on top.
No. Stay with me after class because I want to finish and people have to go. It's already 2 minutes late. Now, the thing is, you can say, well, we haven't finished. No, in fact, we finished the problem because this integral over here is a constant. This is just a number because s is z over x.